Next term is volumetric strain. Volumetric strain is the change in volume per unit volume of a body. So we have, suppose, 3-dimensional body now. The body has 3 dimensions. We are working now with 3 dimensions body. Say this is a cuboid. It is a cuboid which has, say, length L. This is, suppose, height B, and suppose the thickness of this part is T. LBT. The volume of this material is, what is the volume? V will be equal to LBT. And suppose we have applied some forces on this in 3 directions. Suppose some forces are applied or some stresses are applied in this material in 3 directions. Say these are the 3 directions, X, Y and Z. Stress developed in this material is sigma X in this direction, sigma Y in this direction, and sigma Z in Z direction. So 3 directions are there, sigma X, sigma Y and sigma Z, and due to this there is some change in volume of this material, delta V. This is the change in volume. Right? So what is the strain developed in the material? That is epsilon V. This is called volumetric strain. This is called volumetric strain. And how much is this? That is equal to change in volume per unit whatever was the total volume. Change in volume per unit total volume. Change in volume per unit total volume. And it has 3 dimensions, L, B and T. So in X direction we have strain in X direction is, what is strain in X direction? Because length is in X direction, so this is delta L upon L. Strain in Y direction we have the length B, so change in B per unit B, change in B per unit B, this is the strain in Y direction. And what is strain in Z direction? Z direction is T, thickness T, so this is delta T upon T. These are the 3 strains in 3 directions, X, Y, Z. Now we want to relate this epsilon V and epsilon X, epsilon Y and epsilon Z. How we can relate? We know volume V will be equal to LBT. We can take log, natural log on both sides. Taking natural log on both sides. So we can write natural log of V should be equal to natural log of L plus LBT is a multiplication. It will become sum of the natural logs due to the property of log. So log V will be equal to log L plus log B plus log T, right? Because log LBT will be equal to natural log of L plus natural log of B plus natural log of T. So this is the property we have used here. That's it. Now if we differentiate both sides, because we want differentiation, so if we differentiate both sides, we can write differentiating both sides, we can write this is 1 by V into dV, so this is dV by V plus dl equal to dl upon L plus dB upon B plus dt upon t. And what is this dl upon L? This is strain in x direction, this is strain in y direction, this is strain in z direction. And what is dV upon d? This is a change in volume per unit volume, this is volumetric strain. So volumetric strain can be written as volumetric strain in x direction, strain in x direction plus strain in y direction plus strain in z direction. This is an important result which will be used somewhere in our further topics, that volumetric strain in x direction will be equal to volumetric strain in x direction, volumetric strain of the material, volumetric strain of the material will be equal to strain in x direction, strain in y direction and strain in z direction. We were studying the volumetric strain and we have shown that volumetric strain for a cuboid body is given by strain in x direction, strain in y direction and strain in z direction. This we have already proved. Now in this topic, we want to study the multi-axial loading. Means the loading is in x direction, y direction and z direction, and due to that we want to show the volumetric strain in terms of stresses, like stress in x direction is sigma x, sigma y, sigma z, and the Poisson's ratio and modulus of elasticity. So this is our today's topic, multi-axial loading. Multi-axial loading, and due to that we want to find out the volumetric strain. So as in this case we have made a cuboid like this is a cuboid. The stresses are developed in x direction, y direction and z direction. Suppose the stresses are tensile and in x direction sigma x stresses are there. In y direction the stresses developed are sigma y, and in z direction suppose the tensile stresses are sigma z, right? So these are our axes x, y and z. So stresses are developed in all three directions, and we want to find out the volumetric strain due to these stresses in terms of sigma x, sigma y and sigma z. And we have already studied about the Poisson's ratio. What is Poisson's ratio? So we have seen that Poisson's ratio is lateral strain upon linear strain. This is our Poisson's ratio, and this is negative because if the length increases in linear direction, the dimensions decreases in lateral direction, right? So this is Poisson's ratio is actually negative, but we are not writing. Generally Poisson's ratio is given in a positive sense, but actually numerically it is negative value, right? Because these have opposite signs always, epsilon dash and epsilon. As you already know, epsilon dash is lateral strain and epsilon is linear strain. And we want to find out multi-axial loading. Let us think of that if we are applying sigma x, suppose we are considering only x direction, what is the strain in x direction due to sigma x? Strain in x direction due to sigma x. Strain in x direction due to sigma x. What is that? So first case we are taking that strain in x direction due to sigma x. So that will be equal to, that strain will be equal to, suppose I am saying that epsilon 1, that will be equal to sigma x upon E, because our force is, our stress is in x direction and we are finding the strain in also in x direction, and you know strain is stress upon modulus of elasticity. So this is linear strain, basically linear strain, because in same direction we are taking the stress as well as the direction is x. Now there is stress also developed in sigma y, and sigma y is tensile stress. So it will cause the shorten, yeah, decrease in length in x direction. So due to sigma y, there will be decrease in length of the x direction. It means in x direction, sigma y has lateral strain in x direction. So we can say that strain in x, same in x direction, but now due to sigma y. What is the strain in x direction due to sigma y? Say I am saying it's epsilon 2, and that is equal to, now it is not linear because we are finding strain in x direction due to the stress in y direction. So these are opposed and these are perpendicular to each other. So strain in x direction due to sigma y will be a lateral strain, right? And that is equal to mu times epsilon. So that is mu times epsilon. And what is epsilon? Strain due to this, right? So sigma y upon E, mu times epsilon, sigma y upon E, right? So this is the strain in x direction due to sigma y, and this is negative, because the sigma y is tensile and it is trying to shorten in x direction. When it is stretched, the x direction will be shortened, right? So this is lateral strain and this is negative. So I am putting here now the negative sign because we are going to find out the numerical value. So it is better to write here the negative, and this is lateral strain. Now there is also stress in sigma z. So due to that sigma z, there will be lateral strain in x direction again. So we are taking third case, that strain in x direction due to sigma z, due to strain in x direction due to stress in z direction, and these are again perpendicular to each other. So we can write, suppose this is epsilon 3, and that will be equal to, again it is lateral strain, that is mu times, and we are assuming that Poisson's ratio is same in all directions. So this will be negative again because sigma z is tensile, so it will be negative mu strain is stress upon modulus of elasticity. So epsilon 1, epsilon 2, epsilon 3. So what is total strain in x direction? Total strain in x direction, that is the sum of three strains, and this is also lateral strain. So total strain in x direction. So what is then total strain in x direction? This is the sum of these three strains. This will increase, this is positive because it is increasing the length of the cuboid. These will be negative because these have tendency to shorten the length of this cuboid in x direction, right? So we will write the total strain in x direction is epsilon x will be equal to, this is epsilon x will be equal to epsilon 1 plus epsilon 2 plus epsilon 3. So that will be equal to sigma x upon E minus sigma y, mu times sigma y upon E minus mu times sigma z upon E. So this is the strain in x direction. So this you have to remember, this, that the strain in x direction will be stress in x direction divided by E, this is linear strain, and these two are lateral strain. Linear strain has tendency to increase the length of the cuboid, and these have tendency to shorten the length of the cuboid. That's why we have written negative, and total strain will be the sum of these three strains. One is positive and two are negative. Similarly, we will having strain in y direction and strain in z direction. So we will directly write, based on this, using this formula, we will directly write the strain in y direction and strain in z direction. So we will get strain in x direction, y direction, z direction, and then summing up these three strains, we will get the volumetric strain, which this formula is already derived. we have derived that the strain in x direction in terms of stresses and Poisson's ratio is given as sigma x upon E minus mu sigma y upon E minus mu sigma z upon E. This is the strain in x direction, right? Suppose this is our main equation and this is the second equation. Now similarly we can write the strain in y direction. In y direction the linear strain will be due to sigma y and due to sigma x and sigma z the strain will be in lateral direction. So this will be sigma y upon E, this is a linear strain and these two are lateral strains. Similarly we can write the strain in z direction, that this is sigma z upon E. Linear strain, because it is in z direction, we are taking strain in z direction itself, minus strain, lateral strain in x direction minus lateral strain in y direction. And our aim is to find out the volumetric strain in terms of sigma x, sigma y and sigma z. So what will be the volumetric strain? We have seen that volumetric strain we have already derived in the previous lecture, that volumetric strain is equal to sigma x plus sigma y plus sigma z. So here 3 sigma epsilon x volumetric strain is epsilon x, epsilon y, epsilon z, and we have already found out epsilon x and epsilon y and epsilon z. Add up these things. So we will write epsilon y, epsilon v will be equal to, volumetric strain will be equal to sum of these three things. You can see sigma x, sigma y, sigma z by E, this will add up. So we will write sigma x by E plus sigma y by E plus sigma z by E, these will add up. And then here mu times sigma x by E, mu times sigma x by E. So we can write minus 2 mu times sigma x by E, right? Again sigma y by E, sigma y by E, 2 times sigma y by E, mu sigma y by E is 2 times. So minus 2 mu sigma y by E, and then 2 times sigma z by E. So minus 2 times mu sigma z upon E. So adding these we get these things, right? Now volumetric strain will be given as, you can write here that sigma x plus sigma y plus sigma z by E can be taken out now. So we can write sigma x by E plus sigma y by E plus sigma z by E multiplied by, this becomes 1 minus 2 mu. So finally we will get the volumetric strain as sigma x plus sigma y plus sigma z by E 1 minus 2 mu. And this is very important result. We will use this result in many application, many numericals. So this is an important result. So remember it for volumetric strain of a cuboid or multi-axial loading. When there are multiple loads are applied in different directions, then we can directly use the volumetric strain for that body. Previously we have studied the Young's modulus of elasticity, and this is the bulk modulus of elasticity. Suppose we have a cuboid like this, and 3 equal stresses are developed in this material. Suppose the stresses developed are in 3 equal directions, 3 directions, and the stresses are equal in magnitude, and also the nature of the stresses are also same, like tensile stresses are there. Same stresses are developed, suppose sigma, 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 stress sigma and stress sigma. So in x direction the stresses developed are sigma, in y direction the stresses are sigma, and in z direction also the stresses are same, sigma. So direct stresses are applied sigma in this cuboid, right? And due to which there is some strain, volumetric strain in this body. So due to load applied on this bar, on this cuboid, the stresses developed are sigma, and due to that loading, the strain is volumetric strain. So within elastic limit, within elastic limit, the stress developed sigma will be proportional to the volumetric strain. And this stress, this is which is direct stress applied, one of the stress we have taken out of three because all are same. So we have taken the one stress. The stress is proportional to the volumetric strain, and if we remove this proportionality sign, we will get a constant that is called bulk modulus of elasticity, represented by K epsilon V, and this K will be equal to sigma by epsilon V, direct stress, one of the stress upon volumetric strain. So this is the bulk modulus of elasticity. This K is bulk modulus of elasticity. So we can write that, so bulk modulus of elasticity, it is the ratio of direct stress and volumetric strain, right? In other sense, we can say also that if we have a body and the compressive stresses of equal magnitude is acted upon on this body in three directions, say this is compressive stress sigma, same magnitude is there again, sigma in y direction, and in z direction also the stress is sigma. Again, the bulk modulus of elasticity will be K is equal to sigma by epsilon V. This is the same result we will find in this compression also, where we have seen this type of stress element. The application of this is a body submerged in a liquid. If a body is submerged in a liquid, due to Pascal law, you know that due to Pascal law, the stress in all direction will be equal. So if this body is submerged in a liquid, the stress will be same in all directions, three directions, and it will be compressive. The liquid will try to compress the body from all directions, and Pascal's law says that the stress will be equal in all directions. So this application you will find in a body submerged in a liquid. So this is the application of this is a body submerged in a liquid.